Start recording. It isn't actually the chemical potential energy. So if you ever have to define it, you won't have to define it for me, okay? But if you ever should have to, say on an AP exam or something, do not define it this way. I don't think they're going to make you define it because that's not the kind of thing they generally do, okay? When you get into second year university, possibly first year, depending on where you go, they will explain it to you better. But it's part of thermodynamics and my brain and thermodynamics. I can do the first year chemistry part of it. That's okay. Once you get past that, I'm like, I don't know what's happening. There's like, I don't know. Anyway, PV work, whatever. Enthalpy, chemical potential energy. And because E stands for energy, we cannot have E stand for enthalpy. So I guess they just picked a letter in the middle. And so enthalpy is represented by the letter H. Maybe it also kind of stands for heat, okay? But we're not going to define enthalpy as heat because that gets confusing, okay? And of course, capital delta, not lowercase delta, but capital delta. And I think all of you probably know that means change in, yes? So we are often concerned about whether the potential energy was increased or decreased. And so we're looking at a change in the potential energy. So in other words, a change in the enthalpy. So change in enthalpy is given the symbol delta H, change in enthalpy. Now remind me, okay, in an endothermic reaction, kinetic energy is transformed into potential energy. If I was to write a reaction for this endothermic reaction, and I had A on one side and I had B on the other side, where would I put my energy term for this endothermic reaction? Tell your partner. Would it go in the reactants or the products? Okay, that's our energy term, also known as the heat term. And it goes in the reactants because energy is entering the system. Heat is entering the system and being transformed into potential energy. Okay, so heat enters. And is transformed into potential energy. And if it is transformed into potential energy, what can we say about the change in enthalpy? And remember, we're thinking of enthalpy as being potential energy. Yes? So what is happening to our enthalpy in an endothermic reaction? Is it increasing or decreasing? It is increasing. So the potential energy is increasing because we're taking kinetic energy, transforming it into potential energy. Therefore, the potential energy increases. Therefore, the enthalpy increases. And so delta H, the change in H, is going to have a positive sign. Okay, that means H is increasing. Now, if we wanted to graph that, and we put our potential energy on the y-axis and the progress of the reaction on the x-axis, would we start high and finish low, or would we start low and finish high? Have a chat with your neighbor about that. Do we start high and finish low, or do we start low and finish high? Okay, do we like option 1 or do we like option 2? Option 2, yes. Okay, so our endothermic reaction is going to start low and finish high. These are our reactants, which I'm just going to write re. Okay, actually, maybe I'll just write R for reactants. And these up here are our, I have room to write products, so I'll write products, but you could just write P if you want to. An exothermic reaction is the exact opposite. Potential energy is transformed into kinetic energy. And if potential energy is transformed into kinetic energy, what is happening to the potential energy? Tell your partner, if potential energy is transformed into kinetic energy, the potential energy increases or decreases? Decreases. And therefore, what happens to our enthalpy? Enthalpy decreases, because remember, these are, and I'm going to put it in quotes, the same, but they're not really the same. But we're going to pretend they're the same because that makes our life easy. Yes? Okay. So if we were to calculate the change in enthalpy, we would end up with a negative value. Yes? Because enthalpy is decreasing. Okay, and we could draw a graph for that. What goes on the x-axis? Oh, sorry, on the x-axis. Progressive reaction. And what goes on the y-axis? Potential energy. And for an exothermic reaction, do we start high and finish low, or start low and finish high? High and finish low. Those are our reactants. Those are our products. Okay. Now, if we wanted to label the change in enthalpy on this graph, we would say, I would put a dashed line across here so that I know where I'm starting and I know where I'm finishing. And then I would draw a line all the way from the dashed line up to the reactants, or all the way from the reactants down to the dashed line. And I would I put an upwards arrow or a downwards arrow on this thing? Downwards. Whoops. And then I would label that delta H. That is our change in enthalpy. We could also do that for our other reaction. And this time we would put a dashed line across from the reactants. And we would draw a line between the reactants and the products. It should actually touch. Okay, I have people labeling delta H and they'll go like this and they'll be like delta H. And I'm like, that's not really delta H. That's just kind of like an upward arrow that doesn't show quantitatively where delta H is. Okay, so for delta H for this one, should the arrow point up or down? up. Okay, that's our delta H, change in enthalpy.
So it has to be directly from like the gas.
It should go from the reactants to the products. Yeah. Okay, delta H arrow goes from reactants to products. Delta H arrow goes from potential energy of reactants to the potential energy of the products. So the energy term is usually referred to as the heat term. That's your kilojoules in the reaction. So here we have an example, gasoline when it burns. The enthalpy in the gasoline, which is the potential energy essentially in the gasoline, which is mainly octane, mainly C8H18, octane. And if you're into learning your organic chemistry, alkanes, the formula is CN H2N plus 2. So if C is 4, then H is 2 times 4 is 8 plus 2 is 10. And that's because every time you have a carbon, you always have 2 hydrogens for every carbon, 2N. And then you have 2 extra on 1 on each end, okay? So that's how that formula comes about. So if you're interested in that kind of thing, that's how you can find an alkane's formula. I will never be testing you on that, but I'll keep telling you stuff like that because it's kind of interesting. Plus, then when you go and take organic, it won't be brand new to you because I imagine many of you will take organic chemistry. All right. So when we burn gasoline, obviously, we convert the potential energy, the enthalpy, into heat, which we can think of as the kinetic energy. Okay, so we think of enthalpy as the potential energy, and we think of heat as the kinetic energy. Neither of those are very good definitions for enthalpy nor heat, but that's okay. We're going to pretend. So our reactants have a higher enthalpy, a higher chemical potential energy than our products, which have a lower chemical potential energy, a lower enthalpy. And that means our heat term is in the products. And that's going to be, I don't know how many kilojoules, okay? What type of energy is the heat? Kinetic energy. And that is released to the surroundings as kinetic energy. The particles are moving faster, and therefore the temperature increases. So we refer to the kinetic energy term as the heat term. In fact, if you go out in the real world, I don't think anyone else probably refers to it as the kinetic energy term, but it makes so much sense when you're thinking about it that way, especially if you know temperature is a measure of kinetic energy. If you're releasing kinetic energy, then particles are moving faster and it feels warmer. Alrighty. So here, this is just same thing again, and we have our enthalpy diagram, which looks exactly like our what? Potential energy diagram. So the enthalpy diagram is the same as a potential energy diagram. And we call them diagrams rather than graphs. I don't know why, that's what they get called. And usually we label the axis potential energy rather than labeling it enthalpy. Okay? This is the usual label. For the y-axis. And you can see here we've got the delta H is labeled. The delta H starts at the reactants. And where does it finish? It finishes at the products. Oh, yeah, that's okay. You do not need to draw this squiggly kinetic energy line, arrow thing. This thing, do not draw this. I mean, I'm not going to mark you wrong if you do, but it is unnecessary. And if you're doing it like in an AP exam, they'll be like, why are you drawing that? Do you know what I mean? It's just kind of there to remind you, because we're just starting to learn this, that when the potential energy goes down, kinetic energy is released. Since delta H is negative, what does it tell us if delta H is negative? What kind of reaction do we have if delta H is negative? Exothermic. And if you ever have problems remembering that, if you see a negative delta H and you're like, I don't know, is that endothermic or exothermic? Because your brain has just done a little glitch, you can say, I will draw myself a little diagram. And I know delta H is negative, so it has to be going down, right? And if I have a graph that goes down, am I entering the art gallery or am I exiting the art gallery? I'm exiting the art gallery, so it is exothermic, okay? There are two ways to write a reaction to show that it is exothermic. And we've already done the first one, okay, where we put the heat term in the products. So the heat has been produced. We have released kinetic energy. The other way to show that a reaction is exothermic is to write the reaction without an energy term in it and to write the delta H beside the reaction. So you can write the delta H separately. and give the sign. And a negative delta H means the reaction is endo or exo? Exo. One thing I'd like you to notice here. Do you see how delta H is negative? But when we write the heat term in the reaction, we don't write, whoa, what happened there? We don't write minus 5076 kilojoules. Yeah? Our chemicals are losing 5076 kilojoules, but we're also losing, we're giving off 5076 kilojoules. We're also giving off 16 carbon dioxides. We don't write negative 16 carbon dioxides. Do you know what I mean? Like we don't put our products as negative. By having them in the products, that means it's produced. Delta H, though, you have to show a sign. You have to say, so we're starting high, we're finishing low. Okay? Here's an endothermic reaction. And the heat term is in the reactants. Whoops, term. Am I saying things over and over too many times, or is it okay? What do you guys think? I feel like I'm repeating myself a lot. Is it too much? I know you were away yesterday. Am I repeating myself too much? Maybe a little bit? Okay, that's all right. We'll get through this quickly. Okay, so these guys have a lower enthalpy. These guys have a higher enthalpy. And so we have increased the potential energy. So we have increased the enthalpy. And how did we do that? We absorbed kinetic energy and turned it into potential energy. And here's our enthalpy graph. Remember, it starts at the reactants, our delta H. Finishes at the products. Don't draw this. Are we entering the art gallery or exiting the art gallery? We are entering the art gallery, so we know the reaction is endothermic. And the temperature, if we have an endothermic reaction, temperature is decreasing. So two ways to write it: heat term in the reactants, or write delta H separately. With a positive sign. A positive delta H is always endothermic. I'm sorry I'm so repetitive with this. I find when I teach this to regular Chem 11, I have to be this repetitive, like for it to kind of sink in, because they don't hear the word, they just hear endo, exo. Like I feel like I'm just up here, wah, 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 like Charlie Brown. Anyway, have you guys seen Charlie Brown? Like Charlie Brown Christmas? And the teacher talking, wah, 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 wah. Okay. Anyway, do you guys want a few minutes to just do maybe the first couple of exercises in here? Yeah? And then we will move on. We just had a question Does it matter if you draw the dotted line like over here, or what if you drew it like this and did your delta H here? Either way is totally fine, okay? Either way, doesn't matter as long as you're starting at reactants and finishing at products. All right, shall we take a quick look at 6.4c, which is on page 110. You can finish off those questions for homework. Page 110. Okay, so the words system and surroundings are chemical terms. These are specific vocabulary for chemistry. So when we talk about a system, that is the part of the universe we are wanting to focus our attention on, okay? So it's the part of the universe we want to focus our attention on. And generally, the system is a chemical reaction. So for example, if we have 2H2 plus O2 gives 2H2O, the system consists of those molecules. So the system is 2 H's and an O and 2H2O. Okay? If you have a reaction taking place in aqueous solution, let's say we had a beaker here. And let's say we had some magnesium metal. And we put it in there with some AgNO3 aqueous. So we have Ag plus ions and NO3 minus ions. That whole thing, like the solution, all of this would be considered the system. Everything outside of it would be the surroundings, including the beaker. Okay, so everything outside is just considered the surroundings. By the way, oh, shoot. Did I do it wrong? No, I didn't. It's okay. What type of a reaction would we be looking at in this system? Have a chat with your partner. What type of reaction would we be looking at in this system? What type of reaction would that be? What have we got? We've got an element, Mg. And what is the AgNO3? The AgNO3 is a compound. So what type of reaction is that? Single replacement. So what's going to happen is that this would turn into, so the Mg would become 2+. We would still have NO3 floating around. There would be a lot of NO3s. This is obviously not balanced, okay? And what would happen is at the bottom, you would have silver forming. Okay? At any rate, heat would go in or out of that system depending on whether that is an endothermic or an exothermic reaction. Okay? So the surroundings are everything else other than the reaction, the rest of the universe. Okay, so the surroundings are the rest of the universe, everything else. So if that's in gas phase, the walls of the container are part of the surroundings. Everything outside the walls of the container is also the surroundings. Thank you. So if you are the system, let's say I was the system, and I look out at the universe, everything out there is the surroundings. System, surroundings, system, surroundings. Yes? So here we have the system, and then the surroundings is everything around it. Actually, I feel like the flask, no, the system is not the flask. It's the contents of the flask. Or I guess under some circumstances, you could say it's the, I don't know. I feel like that's better. Some chemical reactions release heat to the surroundings. These reactions are what? Exothermic. Some chemical reactions absorb heat from the surroundings. Those reactions are endothermic. So they were literally like if I was to have a beaker and I put my hand on a reaction and on a beaker that had an endothermic reaction happening in it, literally it would be sucking heat energy out of my hand, which is why it feels cold. Okay? If I had an exothermic reaction, it would be literally pumping heat into my hand, which is why it feels warm. Okay? There's a few questions here. You can feel free to answer those for homework, but we're going to move on to 6.4D. And this is maybe the first real completely AP stuff we've done this year.
The what?
This is, no, it's not, because combustion analysis is also AP. Like exclusively AP and not like regular Chem 11 as well, okay? So, although we do a little bit of this in Chem 11, we just do like the first qualitative part, we don't do it quantitatively. Imagine you are holding a pencil. I'm not going to use a pencil. I'm going to use a little cheap chopstick that I have here, okay? And now I'm going to break the chopstick. In order to break that, did I have to put in energy? Yes, I did. So if you remember the pencil, bond breaking, because I broke some bonds here, yes, there were bonds holding it together, bond breaking required an input of energy. Therefore, bond breaking is always an endothermic process, okay? Breaking bonds always requires an input of energy. So bond breaking is always endothermic. Bond forming is always exothermic. Let's imagine that we have a hydrogen atom. Okay, and I'm not going to write H. I'm going to write, we have a hydrogen atom. And we have another hydrogen atom. And it has a nucleus. And zooming around the nucleus, it has an electron. Yes? We have another hydrogen atom with a nucleus, and it also has an electron. Thank you kindly. Now you can imagine as these two get closer to each other, this electron is attracted to this nucleus. And this electron is attracted to this nucleus. Yes? Okay. Now, if I was to put just a positive charge and a negative charge like that, how could I make them, and this is a fairly unstable arrangement, how could I make it more stable? Bring them closer together. Okay, so this is going to come together. So this is unstable. This is more stable. And if it's unstable, what can you say about the potential energy? Potential energy is high. And what can we say about down here with this more stable? The potential energy is low. And in fact, I should have done this one to start with because those could be ions. Okay, so I've got a cation and an anion. And they go from being unstable to being stable. They go from high potential to low potential. And if you go from high potential to low potential, is that endothermic or exothermic? High potential to low potential. That is exothermic. Okay? I'm going to get rid of this little hydrogen atom, and I'm sorry I made you draw it. It is more complex, and we'll talk more about that during bonding. But this just, like, there's a lot of extra forces going on there because there's nuclear repulsion, and there's electron repulsion, and you have to get the balance just right. But when you look at it with ionic bonds, cation, anion, it becomes very obvious that when they're close together, the potential energy has become lower. And for now, can you just believe me that when a covalent bond forms, the potential energy is also getting lower? Okay, we'll talk more about the complexities later. So bond forming is always exothermic because we go from less stable to more stable. So our potential energy is decreasing, so our enthalpy is decreasing, so our delta H is negative, and we are exothermic. Is good? Yes.
So what is the kinetic energy?
What's that, sorry? It's just motion of the molecules. So they'll either be vibrating, okay, or they'll be rotating, or they'll be moving, or they'll be doing one of those things more or faster. Yeah, so that's our kinetic energy, excuse me, is the motion of the molecules.
So when they have high potential energy, they will not move much when they come together again.
They will be moving faster, yes. Yeah. And let's say this was our ionic compound. That heat is going to be released to the surroundings. So it's not necessarily like the particles themselves are necessarily going to be moving faster, but they're going to make the particles in the surroundings move faster. So like if this is happening in a beaker, right? The heat will come out of the beaker and you'll be like, ooh, it feels warm. Yeah?
Without the bonds breaking.
Pardon me, the bond's breaking?
Yeah, it's like formed was, like, argue. Like,
So if I had to rip apart those two ions,
yeah,
I would be going from low potential to high potential, yes?
they all.
So that would be endothermic. Yeah? And Victoria, you had another question.
Like, there's some potential low potential is it a completely equal, chemical combination of energy or some energy releases?
Sorry, could you say that again?
The process of the ions bonding together.
Yes.
Yeah. And that completely, equal combination of energy or some energy releases.
Heat is the kinetic energy.
So the kinetic energy is as well as movement.
Heat is the motion of the particles. Yeah? Heat is the motion of the particles. If you have more heat, the particles are moving faster, which is why it feels warmer.
Are we going to get a strong that it's the end and
They're the same. In chemistry, at this level, they are the same. Heat, kinetic energy of molecules, not any old kinetic energy, but kinetic energy of a molecule, so those are the same. Because heat is basically just vibrational energy, right? It's just like motion, right? Because you've got things that are moving more.
So that would be like other measures of, so you have velocity.
Heat is kind of like velocity, yeah. But it's not just translational motion, it's also, yeah, ooh, I can spin faster, or I can vibrate faster, right? Yeah. Yes.
So, single replacement reaction, there are parts forming and breaking.
Mm-hmm.
But in these cases, there is also going to be endothermic and isothermic, but glass can feel either hot or warm. Hot and cold.
Yep.
So how do you know?
How do you know which? Good question. So glad you asked, because that's where we're going with this. So what Dylan is saying is, here we have our single replacement reaction, wherever the heck it went. It was back here, I guess. Okay. And we had some bonds breaking and we had some new bonds forming, yes? And so we had bonds breaking, endothermic, and we had bonds forming, exothermic. But overall, the beaker is either going to feel warmer or colder. So it depends on the energy contained within the reactants and the potential energy contained within the reactants and the potential energy contained within the products. Are we using more energy to break the bonds than we're getting out with the formation? Or are we getting more out from the formation of bonds than we are using to break it? And that's going to tell us whether it's endothermic or exothermic. And let's go back here because we have pictures, okay? So we're breaking all the bonds in any chemical reaction. This is not exactly how it works, but you can imagine it this way. You can imagine we take all the atoms and we break all the bonds. Do you remember that from the video we saw right at the beginning of this unit, where all the hydrogen and oxygen atoms had to split apart first before they could form H2O? You guys remember that, the explosion? Like 3 people remember that. How many people remember that? Okay, all of you, you're just not nodding. Okay, so all the bonds have to be broken. So we have energy input. And then we have the forming of all the bonds, all the new bonds in the products, and that gives energy out. In a reaction, if we need more energy to break the reactants bonds than is given off by the products bonds, so this is more energy input, and we have, I'm going to put products over here so I don't break the sentence. And this is less energy output. Would that be an endothermic reaction or an exothermic reaction? That's going to be endothermic, okay? And if we have the reverse situation, if we have less energy input to break the bonds, and we have more energy output to form the bonds, then that's going to be exothermic. So we're going to take some CH4. Who is CH4? What's the name of CH4? Methane, okay? Methane plus O2 gives CO2 plus H2O. What is that type of reaction? Combustion. Okay, let's take our CH4. Here it is. And we're going to break all these bonds. Okay? So we have to break all those bonds. We have to break 4 CH bonds. And we have to break 2 O double bond O bonds. Yes? And now all of our atoms are separated. And now we're going to form a bunch of bonds. So we're forming bonds here and here and here and here and here and here. So we are forming two C double bond O bonds. And we're also forming 4 O single bond H bonds. And if we knew the energy required to break each bond, could we calculate the total energy needed to break and the total energy that's given off when formed? If we knew the energy of each bond? Yes, and guess what? There are tables. There are tables that give you the energy of every bond. So you can say, I need this much energy to break 4 CH bonds and this much energy to break 2 O bonds. And that's going to be positive energy, positive enthalpy energy. And over here, I'm going to get negative. Actually, I should say enthalpy because it's the potential energy. Enthalpy. Okay. So, and in grade 12, what we're going to do, yes, sorry.
Can they equal each other?
They can, but it's really rare. Like it doesn't really happen. It would be such a weird coincidence. Yes? Okay. So in grade 12, what we do is we draw potential energy diagrams. We don't just go like this. We actually draw and we go, here's my reactants. And then all the bonds break. Yes? And then all the bonds form. And this is the energy needed to break the bonds, going up to that peak. And these are all the atoms separate. And then going from this peak down to our products, that's when our bonds are being made. That is an exothermic process. So we have an endothermic process and an exothermic process, and we put those together, right? We've got positive, maybe positive 4 and negative, I don't know, 7, right?
So it's overall exothermic.
Overall, it's exothermic. Yeah. So it's endo and then it's exo, but overall it is exo. Yeah? So this is positive, this is negative, and overall it is negative. We could also do the same thing for an endothermic reaction where our bonds broken. We have more positive this time. And we have less negative. And so when we add up the positive and the negative, the overall is going to be positive.
But this totally depends on like the type of atoms.
Totally depends upon the type of molecules, which bonds are being broken, which bonds are being formed. Okay? And like I said, you're going to have a table that tells you the energy contained in each bond. Okay, this is just another one. You can just, it's just, I didn't know which picture was better, so I put both pictures in. Okay, you can look at that one. Okay, here is NaCl gives 2NO plus Cl. So 2 NaCls gives us 2 NOs plus Cl2. These are the Lewis structures. Eventually, you're going to have to draw your own Lewis structures, but you don't really know how yet, so we won't make you. But we start with NO and NoCl and NoCl, and we finish with 2 NOs and 1 Cl2. So we are going to go through this process, and we're going to say, who's being broken? Well, we're breaking... Now, there's actually 2 ways of doing this, okay? You can ignore the bonds that both break and form. Yes, so if we separated all the atoms, we could say we are breaking NCl and NCl, so we have 2 NCl bonds. We could also say that we are breaking 2 N double bond O bonds. We good with that? That would separate all our atoms. Yes?
So basically, you just don't count.
Now, for our products, we are forming a Cl bond. Yes, we're forming one Cl-Cl bond, but we're also forming 2 NO bonds. So it's up to you whether you choose to add the NO bonds into the forming and into the breaking, because they will just cancel each other out. Does that make sense? So what we're going to do is we're going to take a look at a table of bond enthalpies. We have an NCl bond, which is 200 kilojoules. So we are breaking 2 NCl bonds. So what that's going to be, is that going to be a positive value or a negative value if we are breaking the bond? Breaking bonds, are we putting in energy or getting out energy? We're putting in energy, so it's going to be positive. So breaking is positive. So that's going to be 2 times 200 kilojoules. Okay? So the NCl bond is 200 kilojoules. And we are forming, which is going to be an output of energy, 2 Cl bonds. And so that's going to be minus 2 times 243. What? Oh, 1 Cl. So sorry. So sorry. Is good? So our total bond, when the NCl bonds are broken, I've got them backwards. I should have made this blue and this one red. I'll have to go and change that. But anyway, regardless, we have 400 kilojoules absorbed. And so that's going to be positive. And we have 1 times 243 is 243 kilojoules released. So that is negative. And so the total then is going to be delta H is 400 minus 243 is 157. Is good? No? Is not good? We're absorbing 400 kilojoules. We have to put in 400 kilojoules to break the NCl bonds. We get out 243 kilojoules when we form that one Cl bond. Yeah? And so we use 400 kilojoules to break the 2 NCLs. And the formation of Cl releases 243 kilojoules. So that's going to be negative. Okay, that's coming out. And so 400 minus 243 is 157. Yeah? Now, what if you wanted to put in that NO bond, that N-double-O bond? If we look on page 5 of your data booklet, oh, there is no NO bond on there, so that's irritating. So never mind. Hi. Yeah, it's all good. But let's just pretend, can we just pretend that the N double bond O was 150 kilojoules? Pretend N double bond O is 150 kilojoules. We good with that? That would mean that we would also be breaking 2 NO. That would give us another. Is breaking positive or negative? Breaking is breaking endothermic or exothermic? Breaking. Endo. I had to put in energy. So breaking is positive. If I'm breaking 2 of those, that would be plus 300 kilojoules. I don't know why I have brackets there. So 2 times 150, yes? And if I form 2 N double bond O's, that's going to give me negative 300 kilojoules. Do you see how those two would cancel each other out? Yes? So it's up to you whether you put those in or not. I'm not going to give you questions from here today. What I would like you to do is I would like you to make sure you've finished 6.4b and 6.4c, and we'll finish this off tomorrow. Okay? So your homework, finish 6.4b and 6.4c. Hi. Yeah, absolutely.
So when you put in energy, break the bond, endothermic, so
Yes.
what is that energy, like potential energy? Is it
Okay, so the energy I put in is kinetic energy, which is then transformed into potential.
so that transformation is the reason why?
Yes.
So you input heat and then that just transforms.
Potential. Yes.
Oh yeah, so if you were to like experimentally find, or you were to do some kind of experiment, you know the potential energy by the statement, and then you measure the temperature, which is the amount of kinetic energy it has in those forms.
Yeah.
And then you activate the reaction. When you take the temperature, it would be lower your total energy average and lower than your total energy because some energy release surrounding this. If it was executed.
Although in chemistry we don't, like, when we're looking at a reaction, that energy comes out and we just assume it's part of the reaction. Yeah, that's used as part of the reaction. When energy comes in, we assume it's part of the reaction. So the kinetic energy is only part of the reaction.
Okay. So in this ionic form, or like ionic compounds, they have any kinetic energy, or is it just that like a very minimal kinetic energy?
Well, let's think about the particle being non-motionless.
We'll just be good.
If they were motionless, everything would be at 273 degrees Celsius. Because that's where everything stops moving. Everything is moving all the time. The solid particles are jiggling, like everything is moving all the time. We're just using some of the kinetic energy for our reaction. Or releasing some of the kinetic energy. But everything still has kinetic energy. Yeah. So like when these molecules they collide with one another, they're still moving even though they collided. They're just moving a little bit slower than they were before because they collide and they bonds.
So whenever we do equations and we're calculating the energy for reactions, we really only need to look. We're only trying to find the difference in like the amount of energy input and output surroundings.
Yeah.
That's really how I felt. That math is so good. Everything's so better. Like, it's like, and then you got concept. I was home actually. I did this.